Electron configuration. Electron configuration, as you could read, is the arrangement of arrangement of electrons in atoms. I should read it. You would have done this in grade 9. You would have drawn an atom with circles and you would have put dots around and said I can fit 2 dots or 2 electrons in the first orbit, up to 8 in the second orbit, up to whatever in the third orbit, and so on. We're going to do something kind of similar in terms of saying where the electrons are and how many there are in each energy level, but we also have to deal with sub-energy levels. So for us, quantum theory, or saying the arrangement of electrons, is going to be a bit of a different ballgame, but not crazy different. We're going to start with quantum numbers because quantum numbers describe electrons. So let's start with n equals 3. If n equals 3, I can have values of L of this, 0, 1, or 2. I can sometimes, and for electron configuration we will most of the time, write those values of L using letters, which seems like kind of a silly thing at first, but it actually will be more helpful than having too many numbers. But let's put that to the side for now. And then we have m sub L, magnetic quantum number, and that basically tells us the orientation, or the possible orientations of the orbitals. So if I have L equals 1, I can have -1, 0, or 1, 3 orientations. And then what we did was we took each one of those sets of numbers and we said, let's draw a box. So 1 box for the first, 3 boxes for each one of those 3 orientations, and 5 boxes for L equals 2 with 5 possible orientations. And then we started to fill in this page using arrows to represent our electrons. And every time we did it, we started with the first electron in the first box and we worked our way up. Sometimes we filled most of the boxes, sometimes we only filled a couple of the boxes. Let's zoom in on a bit of that for a minute. Most electrons, as you know, have more than one energy level, but every single time we did this, we started with putting electrons in the first box, in the first energy level. We want a tool that allows us to figure out where those electrons go, and reliably all the time, if we can get it, most of the time, if nothing else. Because you remember the problem with Bohr's theory, or one of the problems with Bohr's theory, is that Bohr could not explain the order of fill. So let's think about oxygen. Oxygen, if we were to fill in, we know that oxygen has 6 valence electrons, but we also know that it's in the second energy level. So what we have is 2 electrons in the 1s, 2 electrons in the 2s, and then 4 electrons in the 2p. So I could label my orbitals in that way. I could write the electron arrangement of oxygen in this way. 1s2, meaning the 2 electrons in the 1s, 2s2, meaning the 2 electrons in the 2s, and 2p4, the 4 electrons in the 2p. So the little superscript numbers are now being used to represent how many electrons. The periodic table, as you can see, and as you've known for a long time, has rather distinct sections. And we've got this larger box over with the taller columns. We have more taller columns, and you'll notice I've excluded helium, but we'll talk about that in a moment. And then these short columns in the middle, and then finally the 2 rows at the bottom. And if you pay close attention to the atomic numbers, those 2 short columns on the bottom, those 2 rows on the bottom, actually fit up in row 6 and row 7, but we're going to leave them out on their own for the time being. Now I'm going to show you another periodic table, but I'm going to step out because it's going to fill the screen, but we'll continue to talk about it. So hang on. So here's this periodic table. Now a couple things about it that we want to pay attention to. Number 1 is I've moved helium, at least for the purposes of this periodic table. Still a noble gas, still keeping it in column 18 on the far right, but for our purposes right now, it's more convenient over here. I've labeled those first 2 columns as the S block, and it says n is equal to row number. And the row numbers, as you notice, they're on the far left. I also have something on the far right called the P block, and that says n is equal to the row number again. Middle section, D block, where n is equal to the row number minus 1, and finally those 2 rows on the bottom, F block, n is equal to row number minus 2. And again, every time I say row number, I'm referring to the row numbers as I've identified them on the far left. Okay, let's bring it smaller and I can come back. Now with this periodic table, we are going to be able to use it for identifying or determining the arrangement of electrons, the electron configuration in atoms. Well, how do we do that for, let's say, germanium? Well, for germanium, first of all, we have to find it on the periodic table. There it is, element number 32. So we have to have 32 electrons taken care of, much like we did when we had little boxes to fill in. We're going to start with the first electron. Now, the first electron is going to be the first position. So if I start to think about these these boxes on the periodic table, these elements, not as elements, not as atoms, but if I look at the periodic table now as telling me electron positions. So the first electron will go in the first box, the 31st electron will go in the 31st box, the 23rd electron will go in the 23rd box, and so on. So I start with electron number 1, and I work my way across the periodic table until I can't go any further. So when I start going across 1, 2, I'm in the S block in the first row, and it says that N is the row number. So I have 2 positions. So what that means is I'll have 1, S, 2. 2 spots in the S block of the first row. Well, that's now done, so I move on to the second one, and I have something kind of similar. I start across row number 2, and I'm in the S block again for 2 positions, and in the S block, N is equal to row number. So in other words, I would have 2S2. And now I can jump across the gap and continue on in the P block, where when I'm in the P block, I have 1, 2, 3, 4, 5, 6 positions, so potentially 6 electrons in the P block where N is equal to the row number, so 2p6. Second row is done, start the third row. Third row, again, I have 3s2. And then I'm going to jump across the gap, work my way across the rest of that row. I'm in the P block of the third row, P block, row number is, N is the row number for all 6 positions. Start row number 4. Same place. N is equal to row number in the S block, and I have 4s2. Now I'm doing something a little bit different. I'm going across those short columns where it's the D block. And if I look, it says D block, N is row number -1. So even though I'm in the 4th row, the N value for these electrons is 1 less. In other words, 3d10. And if you count them across, there's 10 electrons, 10 positions. Finally getting close to germanium, I'm back to the P block where N is the row number for 2 electrons. And my last 2 then are 4p2. So I could take all of that and I could write it as the electron configuration, the arrangement of electrons in germanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And if you count them all up, that would be 32 electrons in germanium. Now you're probably thinking, there's got to be a shorter way. There has to be some kind of shorthand because that, as long as it was only 32 electrons. What about big atoms? Well, there is a shorthand way. And what we'll do is we'll use the end of the previous row, which is the noble gas. We'll use that in square brackets to represent most of the core electrons. And then what we do is we finish off the final row. So if you were to look at germanium, then the previous noble gas to germanium is argon. That takes care of, I believe, 18 electrons. And then the remaining, whatever you need to get to 32, we write down specifically with our 4s2, 3d10, 4p2. So let's try that for bismuth. So first we find bismuth on the periodic table. There it is. Lots of electrons. If we were to start from this top at hydrogen, we'd be doing a lot of writing. We are going to start from the top, but we know that electrons are going to fill atoms in a similar way each time. So what we'll do is we'll take our previous noble gas, xenon, and we'll use that in square brackets to say our core electrons, we know are going to be all the same. They're going to have the same electron configuration as a xenon. Then we do our last row, row number 6, and we start with 6s2. Then you'll notice that if you keep count on the atomic numbers, we go to electron number 57, and 58 is somewhere else. So we do our 5d1, and then we cut across one of the last rows down here in the F block. If you count them up, there are 14 electrons. And then we go back to the 5d for the remaining 9 before we get to our 6p3, taking us up to the last electron of bismuth. Now, you could write that information as the electron configuration exactly as we did it using the periodic table. Or you could say a d electron is a d electron, a d orbital is a d orbital, and you could combine those 1 and 9 d electrons to say 5d10. Either way doesn't really matter to me a whole lot. Now, we colored in chromium family and copper family a little bit different from each other, and you might be wondering why. We'll talk about that in class, but basically what we're going to do is we're going to look at our orbital box diagrams. We're going to compare our, what we know about behaviors of atoms and properties of atoms, and we're going to see that those two families do something different, but predictably different. So we'll take care of those. We're still going to do the electron configuration for them almost the same, but they've got a unique feature that you will be expected to know. But we'll talk about that in class, and we'll take care of it at that time. Anyhow, see you later.